Hi, this is Alex Trujescu, and I'll talk a little bit about convex hulls and how they can be used to estimate material stability. I learned about this topic while a postdoc in a material science department, and one of the things I realized is that it's not usually covered in either chemistry or physics departments. So it seems like a pretty useful topic. And first, a brief comment, I'm an assistant professor at the Indiana University Bloomington Chemistry Department. So, we're welcoming applications from a variety of backgrounds, whether chemistry, physics, material science, chemical engineering, all variety of backgrounds are welcome if you're interested in working with atoms and electrons. So my own degrees are all in physics, plus one material science postdoc and one physics postdoc. Unsurprisingly, I'm in the physical chemistry division, also materials and inorganic. So the point is, yes, apply it to our department if you're interested in the types of stuff I talk about in these videos. All right, so convex hulls in material science are basically a quick estimate of material stability. So, let's think of the energy of putting two planets together, a sort of energy per planet. You can estimate it as the energy of the whole system minus the energy of each planet individually over two, right? It's an energy per planet. And the point is that things like, whether you have some planes moving around, right? Some sort of kinetic energy from that, or buses or whatever, it's both in the planet and in the final system. So, that doesn't really end up mattering. It's really the energy of putting things together. Well, it might have some small effect, right? But anyway, if you have three planets, again, you have an energy of the entire system, minus the energy of all the planets added up, and then you have this per planet. So, it's a weighted average, of course. So what does this have to do with atoms and materials? Okay, well, let's think of first the relative energy of some compound made only out of atoms A, but itself is just zero, right? It's just itself. And for B, it's the same. There's a little bit of a difficulty in how you define this energy of A. So for example, if you have oxygen, the lowest possible energy, would be the energy of like half an oxygen molecule. For something like copper, it's relative to one atom of copper in a solid of copper only, right? So, this definition can be a little bit tricky. But then if you have a material that is half of each in composition, well, you take the energy AB minus the energy of each individual material, and you divide this by two, right? So this is a sort of average energy of putting things together. And here, this is positive. So this material, AB or molecule, would just decompose into A plus B. But if you have it in some sort of other crystal structure or something like this, and it's below, then it's stable relative to, A and B, the pure compounds, or the end members if you want. So then we can connect the lines, right? And this is what defines our little convex hull with these three materials. On this line, the lowest line, materials are considered stable. Suppose you have something that's three A atoms and one B atom. Well, here in this dot, if it has this energy, even though it can decompose into A plus B, it can decompose into A and AB, right? It's as if these two are the end members and this is above this line. But if you have a different crystal structure that has this energy, this one can't decompose into these two. So you now update the convex hull. So in practice, you keep doing calculations, you keep adding points, and some of them will update the convex hull, and some of them will be here and will keep just having unstable structures. So this can keep going. It's hard to get right. It can be difficult to find the lowest energy electronic structure for given structure, composition. This depends on the functionals, things like spin order, spin orbit coupling, things like this. Well, this should be a structure for given composition, right? But anyway, all these things matter, and all the errors in your calculation, or they are limitations. The functional you use, just everything. And this doesn't even take into account pH, temperature, right? This is a 0 Kelvin thing. All of these things end up mattering, and there's ways to go beyond this. But as a general rule, you see something that has 1 eV above the convex hull per atom, that's probably not going to be stable, just to put it mildly. And you can look at actual examples in, high throughput databases. So this is OQMD from Northwestern. And, you can look, for example, at the titanium oxygen convex hull here, see the stable polymorphs. If you've never heard of the term polymorph, it's basically the same as an isomer, but for a crystal structure instead of a molecule. Anyway, and for each particular composition, because in DFT things tend to be integers, you're going to have, in integer number of atoms, you're going to have these columns. And the lowest one is the stable polymorph, and so on. And some compositions will just not be not have a stable structure at all, and that's fine. But each vertical line is the same chemical composition. This is the equivalent and materials project between titanium and oxygen. Here it's different order, but the basic point is you can look at a convex hull, and you can also look at the energy above the hull for, say, this compound. And you can also look at whether it's been experimentally observed, which is quite different. But, the two are, like I said, convex hulls aren't perfect, but they're quite correlated with experiment. And convex hulls can be multidimensional. So you can have, say, strontium titanate, strontium, titanium, and oxygen, and you can have all these different compositions. And this is basically seen from above, and you have a bunch of triangles instead of lines at the bottom. But the basic point is the green dots are, green circles are the stable polymorphs, and the red ones are not. And then here, this is the equivalent for materials project, which is more interactive. So you can't actually see here all the dots, you have to hover over them. But anyway, this is how things look like. So yeah, thank you for watching this video. This is my group website. So yeah, look forward to hearing from you. Thank you.